Now we'll get to see what this is about. Use the Laplace transform to solve the initial value problem 2 dy dt plus y equals 0, and the initial condition y of 0 is equal to -3. Now this is a linear first order differential equation or initial value problem. We can solve this using techniques that we saw in the very first set of videos. But this is about using the Laplace transform, which is necessary in some cases. I'm not trying to tell you it's necessary right now. Our basic plan, I'm going to call this plan part 1, is to apply the Laplace transform to both sides. And right now what that looks like is 2 times the Laplace transform of dy dt plus the Laplace transform, I'm going to call it y of t, and equals the Laplace transform of 0. We'll talk more about this as we go, but I want to remind you that when we apply the transform to functions of t, we end up with functions of s. So I'm going to draw a little diagram over here. We start with an unknown function y of t. That's where we are here. We apply the Laplace transform, and we end up with functions that involve s, and we're going to call this uppercase y of s. The effect of this is a bunch of expressions involving s that we then manipulate. We will end up solving for y of s. I'll show you what that looks like, of course. And then, once all is said and done, we're going to apply the inverse Laplace transform and bring it back to functions that involve t. You can think of this s area, this y of s area, as kind of like a playground that doesn't really exist for what we're doing. All of the stuff that we're working with exists in the realm of t, in the time domain. In other applications or other disciplines, you might care about what's going on in the s domain, but for us, that just allows us to manipulate expressions that are algebraic. And in order to see what I mean there, we have to talk more about what we just wrote down. 2 times the Laplace transform of dy dt. And right now, we're already stuck. We don't have a transform for a derivative, but that's where we are now. We're going to look at how to transform a derivative. I know we're looking at this as dy dt, but I'm going to develop this in terms of f. The Laplace transform of f prime of t, by definition, is the integral from 0 to infinity of e to the negative st times f prime of t dt. We integrate this using integration by parts. Usually I let dv be e to the negative st. I'm not going to do that this time. This time u is e to the negative st, so that du is negative e to the negative st dt. The reason for that is I'm making dv f prime of t dt. I don't know what f is, but I know that v is then f of t, right? So that works out pretty nicely. Using our integration by parts formula, that's going to give us f of t divided by e to the st evaluated from 0 to infinity plus s times the integral from 0 to infinity of e to the negative st times f of t dt. Now, if f of t is of exponential order, then f of t over e to the st approaches 0 as t approaches infinity. So evaluating that at infinity gives us 0. We subtract what we get from evaluating at the lower limit, and that gives us negative f of 0 plus s times, and if you look at this integral, folks, it's exactly the integral of the Laplace transform of lowercase f, which I'm going to write down as uppercase f of s. We now have a formula. The Laplace transform of f prime of t is equal to s times uppercase f of s minus lowercase f of 0. Now I hope you can see some of the value in the notation that we're using here. Uppercase f tells me that I'm in the s side, having transformed something. Lowercase f tells me I'm dealing with the t side. Having this f of 0 makes it really nice when we have an initial condition for when the independent variable is 0. Let's go back to our plan. Plan part 1, apply the Laplace transform to both sides. Plan part 2, solve for uppercase y of s. And then plan part 3, use the inverse transform to find y of t. So let's look at this process again. We had started with 2 dy dt plus y is equal to 0, and the initial condition y of 0 is equal to -3. We have this formula for the transform of a derivative, and so we can replace dy dt. We're applying the transform to both sides. We aren't replacing dy dt. It will look like s times y of s, because that's the function we're dealing with, y, minus y of 0. Now 2 is in front of that whole thing, so, be mindful of that. Plus, we have this y here. I don't know what the Laplace transform of y is, but I know what I can call it. It's uppercase y of s. And then the Laplace transform of 0 is 0. We have this initial condition that y of 0 is equal to -3, so we get to substitute that in place of y of 0, and we end up with 2s y of s plus 6 plus y of s is equal to 0. So we have applied the Laplace, where are we? We've applied the Laplace transform to both sides, and now we're going to solve for y of s. We have y of s in two terms, combining those, and then factoring out the coefficient gives us 2s plus 1 times y of s. And then I want to isolate y of x, so I'm going to subtract 6 from both sides. That's going to give us that y of s is equal to -6 over 2s plus 1. We don't have a transform rule for 2s plus 1, but we can factor the 2 out of the denominator, divide it into the 6. So y of s is equal to -3 over s plus 1/2. Applying an inverse transform rule to this gives us that y of t is equal to -3e to the -t over 2. And folks, that's what this has been about, and that's what this process looks like. Now that we've seen the process, I want to step back and talk about it. I'm going to go back to this diagram here. We started in a land of t's. We Laplace transformed and found a land of s's, and then we brought it back to the land of t's. But what we did was we started with a differential equation. That equation had a derivative in it. And when we applied the Laplace transform, we had an equation that only had algebraic components in it. And we manipulated things algebraically. And then we brought it back to the land of t, which I'm going to call the real world here. So the Laplace transform allows us to take a differential equation and turn it into an algebraic equation. And that's where its utility is for us.